Okay, this P6 revision video is about the Rutherford alpha scattering experiment and the evidence it gives us for the structure of the atom. Okay, so we need to be able to explain what the experimental setup is for this Rutherford alpha scattering experiment. And what you have to have is a vacuum inside a closed chamber. You need a thin gold foil mounted inside the centre of that chamber, and you need a source of alpha particles. Now, at this point in history, scientists didn't know about neutrons and protons, so all they knew was the alpha particles were positively charged and a fairly reasonably large mass compared to something like an electron. And an example of an alpha source you could use here would be something like polonium. Okay, and then you need a way of detecting the alpha particles, and this red thing on the right hand side here is the detector, and the detector can be moved in an arc around the outside of the experiment, so it can detect alpha particles that had hit the foil and come off in any direction. And this experiment is pretty much one of the earliest experiments where you couldn't directly look at a nucleus because it's too small, or couldn't directly look at an atom because it's too small to see under a microscope. So this was a way to sort of indirectly get some evidence for what the structure was like by looking at what happened when we fired these alpha particles at the atom. And Rutherford had an idea of what would happen because there was a model of the atom at the time. Okay, and he was interested in what would this thing called the scattering angle would be, how much of an angle of deflection these alpha particles would experience when they went through the gold foil. Okay, so the model he was using at the time to base his ideas for this experiment on were this thing called the Plum pudding model. So scientists knew that atoms contain electrons. Electrons had been discovered, and they knew that electrons were negative. Right? They knew that overall the atom had no charge, so that made sense then that whatever the rest of the atom was made of had to be positive to balance out the negative for the electrons. And the idea for the plum pudding model then was that the electrons were like plums, stuck in a big blob of positive charge, which was the pudding. Okay, and then these big round sort of pudding-like atoms would stack up together to make materials. It's worth noting also that they did also know that the electrons were very light, so most of the mass of the atom would have to be in this pudding part, not in the plums, which were the electrons. So that was his model of the atom that he was using. So he actually gave this experiment to his research assistants, these guys called Geiger and Marsden, to do, and he said, go away and confirm the plum pudding model for the atom, and then, you know, everybody will be happy and it'll be lovely. So what they expected to happen then when they put the alpha particles through the gold foil was that pretty much all of them would go straight through the foil with very slight deflections. And the reason for that is that the plum pudding model has all the charges spread out. The electrons are sort of in different places in the atom, and the positive charge is spread out over a big area. It's not concentrated in one place. What that means is that the static force between the atom and the alpha particle that was coming in would be quite weak. Okay, and there'd be very little force there because of this spread out charge, and so most of the alpha particles would just go straight through and be very unaffected. So that's what they were expecting to happen. Okay, they were expecting to put the detector in the straight through direction and all the alpha particles would go there, and when they moved the detector around to other locations on the outside of this chamber, it wouldn't see any alpha particles at all. But they needed to check, because that's how science works. So what they actually saw, or rather what Geiger and Marsden saw, was indeed most of the alpha particles carried on straight through the foil, but when they moved the detector around, they saw a small fraction that were deflected through quite a large angle, so that scattering angle was quite big for a handful of these alpha particles. And then even more astonishingly, they saw a very, very tiny fraction that got deflected back the way they came. And this was so surprising that Rutherford famously said that this was a bit like firing a tank shell at a piece of tissue paper and the tank shell bouncing back at you. It seemed really, really amazing that this had happened. So when this happens in science and you get unexpected results, the only conclusion you can draw, especially if the results have been confirmed and you've checked the experiment, is that the model you're using to make your predictions isn't correct. So that's what Rutherford said. He said, well, the plum pudding model can't be right then. We have to have something else, okay? And a new model was needed. So this is what he came up with. We're going to do a side-by-side comparison of the two. So just to remind you, the plum pudding model, the electrons of the plums embedded in the big positive pudding. The mass and positive charge are spread out because the pudding is spread out. And the low mass electrons are stuck in it, right? So Rutherford's proposal was really the first idea of what we call the nuclear atom. So the electrons are still there, but we have the mass and positive charge concentrated in a small central nucleus, okay? And the electrons kind of orbit around the outside, a bit like planets orbit around the sun. And most of the atom, therefore, is empty space. Okay, because all the mass and charge is concentrated in the middle. So that's his new model, but we need to make sure we can understand how that new model does explain the results of his experiment. So to do that, we look at alpha particles coming in towards a single atom. Now in the real foil, obviously there's lots and lots of atoms, but you can get an idea of what's going to happen just by looking at one atom. So on the left hand side here, we've got 3 alpha particles in different positions. Now we have to be clear, the alpha source, we can't direct the alpha particles in a particular direction. They'll be randomly hitting the atoms in different places all throughout this experiment. So there was no control over exactly where the alpha particles went. But you can be assured that all of the possible locations that an alpha particle can hit the atom at will have happened if you wait long enough during the experiment. So we'll see all possible paths for the alpha particles. We're going to concentrate on 3 that kind of illustrate the ideas we're looking at here. So starting off with this one at the bottom here, okay, we're going to ignore the electrons as well because we've already said the electrons are very light, so they're not really going to deflect the alpha particles. They just get knocked out of the way by the alpha particles. And indeed, that's why alpha particles are so ionizing. They just sort of rip the electrons off these atoms, and the electrons don't deflect them really very much at all. So we're going to get rid of those and just concentrate on the effect of the nucleus, which is where the positive high mass part of the atom is. Okay, so that first alpha particle comes in, and because it gets very close to the nucleus is positive, the alpha particle is positive, and thinking back to P5, that means they will repel each other. And that is the path that it followed, and the idea is that because this particular alpha particle happened to go extremely close to the nucleus, it experienced a very large repulsion force back the way it came and slightly off to the side because it wasn't quite hitting it head on. But that's extremely unlikely, right? And the reason that's extremely unlikely to happen is because the nucleus is very small compared to the size of the whole atom. So you have to be sort of very lucky to get that alpha particle path to happen. Slightly more likely is the next path, right, where the alpha particle sort of just has a near miss with the atoms. It's not really heading towards the with the nucleus. It's not really heading towards the nucleus, but it goes fairly close to it. And because it goes fairly close to it, it still experiences a reasonably large force, not enough to deflect it back the way it came, but it gets nudged off to the side, and so there is a significant deflection here. Again, that's only a small fraction of them. Most of the alpha particles, because the size of the nucleus compared to the size of the atom is so tiny, almost all the alpha particles will completely miss the nucleus, go nowhere near it, so they'll experience a tiny, tiny force and therefore a tiny bit of deflection. Okay, so those are the 3 situations. And if we think back to our picture of the alpha particle experiment results, I've taken the labels off, these were the results, you can see how these match up. Okay, the vast majority of the alpha particles going straight through matches up to that top path there. Okay, the small fraction being deflected matches up there, and the very, very tiny fraction that happened to hit the nucleus almost head on, right, corresponds to that path there. So there's the link between the Rutherford model of the atom and the results of his experiment. Okay, So you need to be able to explain how those two things link together. And finally, just some features of the experiment and the observations and the explanations that go with them. If you just pause the video for a second, see if you can work out which of these explanations on the right hand side match up to the experimental details in the setup of the experiment, or the observations of the experiment on the left hand side. Okay, and then when you unpause, we'll just check the answers. Okay, so the top one, the experiment takes place in vacuum. Well, this refers to something else you need to know for P6, and that's namely that alpha particles are extremely weak at penetrating through things. They can only travel a few centimetres in air. So if your apparatus was filled with air, the alpha particles wouldn't even get to the gold foil in the first place. Okay, and then you'd detect nothing. So the gold foil, therefore, also needs to be very thin for very similar reasons. If we made the gold foil thinner than even a few atoms thick, then the alpha particles would all just get absorbed in the gold foil and none of them would go through, and we wouldn't see any results of the experiment. So those two are the experimental setup ones. We've already said this one. Next one, most of the alpha particles travel straight through the foil. Well, that one is already in the correct place. It's because the gaps between the nuclei must be large compared to the size of the nucleus. So that's really all. You can also say that as the size of the atom must be large compared to the size of the nucleus. A small fraction of the alpha particles show a large deflection. Now, these last two are a little bit tricky. The large deflection actually only requires the nucleus to have a lot of mass. If the nucleus was negative, we know it's not because we know the electrons are negative, right? And the nucleus has to be positive to make the atom neutral. But if the nucleus was negative, we could still get these large deflections. The deflections would just be in the opposite direction. However, to get the alpha particles to bounce back, it would be really quite unlikely to get the alpha particle to kind of slingshot around the nucleus if it was negatively charged. So the fact that they bounce back really tells us that the nucleus has to have a positive charge, and just like the large deflection for the ones that go forward, it must have a large mass as well. So those are the explanations and how they match up. And a likely scenario in which you'd get to talk about the Rutherford alpha scattering experiment is 6-mark questions. You might be asked to explain the setup and the results for 6 marks. You might be asked to do this kind of matching activity. But you need to know it in enough detail that you can draw a diagram as an excellent plan if you're asked to describe the setup, so that you can then refer to the diagram, and sketch the results on the diagram as well would be very, very useful and save you quite a lot of time and get you lots of marks if you were doing it in a 6-marker. So remember, don't be afraid to draw those diagrams that we've shown, both the experimental setup and the paths of the alpha particles, those 3 paths that we did compared to the nucleus.